Hello and good morning. Yeah, so I will present results from scenarios that look into stabilization at 1.5 to 2 degrees. So this is work done in a major research effort with colleagues from my institute, the Potsdam Institute, as well as other research institutes around the world. I should mention that this is much of the work, or the results that I'm showing are still based on a paper review, so please do not cite or quote or Twitter at this point, but we are hopeful that this will come out over the next couple of months. So let me start with a bit of geophysics to motivate why low stabilization is so important. So let's look at the temperature curve over the last 20,000 years. So there are two insights to take from this. The first is that the climate was remarkably stable over the last 10,000 years over the last Holocene, just until about 100 years ago when humans started to burn fossil fuels at large scale. The second insight is that if we go yet 10,000 years earlier until 20,000 years ago, when the last glacial maximum happened and all of Norway was covered by a huge ice sheet that actually extended all the way until northern Germany, we were only 3 degrees below present warming levels. So if we continue to burn fossil fuels, there are different scenarios, but we might be in for warming of, let's say, 4, 5, or in the most extreme scenarios, even 8 degrees. So given that -3 degrees makes the difference between our current climate and an ice age, it shouldn't be a surprise to us that warming by the same amount into the positive direction, we should see similar changes to the global system. And this is a key concern that motivates us to pursue stringent climate targets. So for example, the ice sheets of Greenland, of Antarctica, would be put at risk if we have major warming, and this is what we refer to as tipping points in the climate system. So the Paris Climate Conference or the Paris Agreement led to the conclusion that humanity should pursue or should aim at limiting warming to well below 2 degrees and even pursue effort to limit that warming to 1.5 degrees, which would not entirely eliminate the risk of this tipping points, these large-scale major changes to the climate system, but at least reduce it to the extent possible. So a second insight from the geophysical climate science is that global warming is largely determined by the cumulative amount of CO2 deposited to the atmosphere. So it's not about the flow of emissions, but really the aggregated amount of CO2 over time. So if we want to pursue any kind of climate stabilization target, that means in the very long term, we need to get to close to zero emissions because there's a finite residual budget for CO2, which is around 800 gigatons of CO2 from now if we want to stabilize well below 2 degrees. If we go for the more ambitious target of limiting warming to below 1.5 degrees, we are even in for a budget of around 200 gigatons of CO2, and this is extremely tight given that our current emission levels are around 40 gigatons of CO2. So in the medium to long term, we really need to get to near zero emissions, anthropogenic emissions. So how can that be pulled off? We, in this study, looked at an ensemble of integrated energy, economy, climate models to study how such 1.5 degree stabilization can be achieved. This is of extremely high relevance currently in the scientific community because the climate conference in Paris also asked the international panel on the Intergovernmental Panel on Climate Change to produce a special report on the 1.5 degree scenario. So these are total CO2 emissions that I'm showing here for such 1.5 degree scenarios with a few important features. The most important one is we need to peak and decline emissions as soon as possible by 2020, and achieve quite heroic emission reductions until mid-century, about carbon neutrality around 2050, 2060, and then go into deeply negative emissions over the second half of the century. So what does it mean? It's quite helpful to break this down into two components. One is the residual fossil CO2 emissions on the one hand side, and on the other hand, these emission components from land use and the combination of biomass with CCS. So if you use biomass, for example, burn it in a power plant, extract the CO2 from the exhaust stream and store it geologically, you can achieve negative emissions. And this is a mechanism that, as I will show in a minute, is very important for such 1.5 degree scenarios. So to further understand what the implications of such stabilization are, it's quite helpful to look into a sectoral breakdown. I said 1.5 degrees implies around 200 gigatons of residual cumulative CO2 until the end of the century. And if we look now what these scenarios do, these very ambitious scenarios that are as optimistic as it gets in terms of policies, saying like in 2020 we'll reach a peak and then there will be a global effort towards strengthening emission reductions. Still in these scenarios, we have around 300 gigatons of CO2 from the energy supply side. And on top of that, quite significant amounts of residual emissions from burning fossil fuels on the demand side, for example, in industrial processes, in the transport sector, or for heating buildings. If we then want to go down to 1.5 degrees, obviously we need a substantial amount of negative emissions, either from the land use sector, for example, from afforestation, or via this mechanism of combining bioenergy with carbon capture and storage. An important insight from these scenarios, and actually from scenarios in general that have this very deep decarbonization, is that there's a substantial difference in how decarbonization plays out on the supply side and on the demand side. So the electricity sector plays a key role here. And what I'm showing are scenarios for three types of decarbonization scenarios. A medium 2-degree scenario, which has around 50% likelihood of limiting warming to below 2 degrees. Then a so-called well below 2-degree scenarios, which has a greater likelihood and ends at around 1.7 degrees by 2100. And then these very stringent 1.5 degree scenarios, which manage to limit warming to below 1.5 degrees by 2100. The insight is, no matter what you do, and this red shading above is emissions that would occur if we just pursue current policies. No matter how these scenarios are, or like the stringency of the climate target, you really have to go achieve close to 100% reduction in your electricity supply. Demand side looks different. There it's a lot harder to reduce emissions. For example, in transportation, we have there's difficulty, or there's a limited potential for electrification of transport in freight or in aviation. Industrial processes, not all of these can be electrified, so there's a significant residual emissions on the demand side. So really the big difference between 2-degree scenarios and 1.5-degree scenarios is that you really have to ramp up these more painful emission reductions in energy demand. So towards the end, so far I discussed these very ambitious climate policy scenarios that assume that in 2020 you would have a strengthening of current policy efforts towards a global emission reductions in line with the 1.5 degree target. Of course, the world is currently on a different track, and this different track is shown in this orange shading. The Paris Agreement has introduced this mechanism of nations putting down their mitigation plans until 2030. We kind of extrapolated those into the future, very similar to the new policy scenario presented by the IEA. And that leads to a stabilization of emissions over time, but not a reduction. What we would need is this very deep reduction. And by 2030, we already are looking at an emissions gap of around 20 gigatons of CO2. If we don't achieve the strengthening of 2030 emission reduction efforts, there are two things that are happening. First is we have additional emissions until 2030, but then secondly, after 2030, it gets harder to reduce these emissions because of the lock-in into a fossil-intensive, further lock-in into the fossil-intensive system that we are still in. Looking at this through the lens of the budgets, we can consider these cumulative emissions from now until 2030. So looking at this early action scenario and the delayed action scenario, and of course, there's a bit of extra emissions from this delay. If you then look at 2015, the longer term, this difference between the early strengthening and the late strengthening increases. And this is precisely because of these carbon lock-ins. In terms of sectoral decomposition, you see that there's a lot of red shading. So this is really carbon lock-in into, for example, coal-fired power plants. And there's also extra emissions from the industrial sector because you really have like these long-lived infrastructures that you haven't adjusted to a low-carbon world in time. And then in the very long term, this difference between early action and late action grows to around 300 gigatons, also because the world is not prepared to the scaling up of negative emission technologies like bio-CCS that would be required for 1.5 degree stabilization. So coming to the conclusions, the achievability of these very low stabilization targets, 1.5 degree in particular, but also 2 degree target really hinges critically on the residual fossil emissions from the energy system. And these will also ultimately determine how much carbon dioxide removal we need from bio-CCS and other land use options and the associated sustainability impact. So there are a lot of concerns about what that means for biodiversity, what it means for food security if we heavily rely on biomass for the climate stabilization effort. We estimate that around 1,000 gigatons of CO2 is like this lower limit of how low we can get with our residual CO2 over the 21st century. And this lower limit is determined, A, by how fast you can, the pace of decarbonization, especially of electricity supply. It's very important to act early and go after these low-hanging fruits that you have in the electricity sector, which is so cheap, is relatively cheap to decarbonize. But then also, it depends on how innovative we are about decarbonizing the demand side, about electrifying transportation, for example, thinking about novel approaches of electric trucks, for example, or low-carbon processes in industry. And thirdly, of course, lifestyle changes. So to the extent that we can slow down final energy demand growth and the growth of material demand on a global scale, to that extent, the effort will be smaller. So what we see is that 2 degrees still is barely achievable without large-scale biomass and CCS deployment. This is no longer true for 1.5 degrees. So this is not a choice. If you want to go for 1.5 degrees, it's no longer a choice to do carbon dioxide removal or bio-CCS. It's really a geophysical necessity. And then not strengthening efforts towards deep decarbonization is increasing the lower limit of these fossil emissions by around 300 gigatons of CO2, and that's going to push the 1.5 degree target out of reach. And at the same time, not strengthening efforts until 2030, from this 2030 viewpoint of current policies, reaching 2 degrees will be as challenging as it looks like, or as the 1.5 degree target is from the current perspective. Thank you.
Thanks, Gunnar. Please sit down. Can we keep that slide up because it's quite a useful... Oh, The last slide up, can we have it back up, please? This is quite a useful kind of aide-memoire of Gunnar's conclusions. I think we've got a question already. Thank you very much. Reinhard Madlena from RWTH Aachen. Please, Reinhard.
Try to get the micro on. I think what you showed tells us nicely that there is also an issue of large-scale versus small-scale solutions. If we need BECCS, biomass CCS, there is a question, is this more competitive, or is it competitive at all against natural gas CCS? And it's a large-scale technology which needs large-scale plants, large-scale pipeline infrastructure, etc. And that needs long lead times, long construction times. And so my question is, do you see that realistic to get it done from that perspective of lumpy investments versus many modular technologies which can be ramped up much more easily?
Excellent question. So I think what we see from that is if you really talk about 1.5 degrees, and this is the point of the study, so that for the international community, we want to spell out the requirements of what it takes to do 1.5 degrees. And the answer would be regarding lumpy versus kind of more granular-sized technologies. For 1.5, you need both. You definitely need these large-scale transformations on the demand side, which would mean electric vehicles to a large extent. You need this fast, deep decarbonization of power supply, which we largely would rely on renewable energy sources. Again, PV is a small, nice, granular-sized technology. That's why it's so successful in its innovation. But we can also show that this is not enough. So if you would really want to go for 1.5 degrees, you also need large-scale approaches like biomass and CCS. And maybe also following up to the earlier discussion, CCS, as we see it, comes in very different flavors. It comes as CCS in the power system with coal or gas. It comes as CCS in the industrial sector, or it comes as CCS in combination with biomass with this extra option of reducing emissions. So my hunch is that really the most important flavors of these CCS technologies are bio-CCS because of the strategic value of the negative emissions. On the power sector, it's not as important. You have the other options. You have nuclear, you have wind, you have solar, which are quite promising options, and which end up having much lower specific life cycle CO2 emissions. So we have a new study out that shows precisely that gas and coal with CCS still has very high residual or comparatively high residual emissions, and this ends up being too much for 2 degrees. So that's why these other options, industry with like CCS with industrial processes such as steel and CCS with biomass end up being more important.
And what about the timing of the lumpy, as you call it, the lumpy technologies? Yeah. I mean, can you actually meet these scenarios if you don't have activation, as it were, of the lumpy scenarios quite soon?
Yeah, this is actually...
You're hoping that they're going to kick in by 2030, 2040, so when do they have to start?
Right. This is exactly what this slide is trying to show, is it really matters, like in terms of scale, bio-CCS will not contribute much by 2030 or 2040, but it matters that we now start into researching this option and kind of, starting with demo plans, starting with the development of these options to have it in our portfolio by 2040, 2050 for large-scale deployment. And if you don't do that, and this is what this delayed action scenario does, really it hurts your long-term potential of bio-CCS just because you have waited for another 10 years before you kind of start researching into these technologies.
Asger.
So we are a bit short on policymakers on the stage today, but this is streamed, so of course we can still give some advice to the policymakers. And based on your insight in the 1.5 degree and 2 degree scenarios, what would be the immediate actions that these policymakers should start doing today? What are part of a robust solution that we would always find in a successful 1.5 or 2 degree scenarios? So if actions are to be taken tomorrow, what is the most urgent and most robust action to take?
Well, a very important insight is that if you try to go for 2 degrees with very limited reliance on biomass and CCS, or if you go for 1.5 degrees, your near-term actions are very similar. And this is really phasing out, like the first big step is decarbonizing power supply. This is absolutely essential. Second is scaling up these demand-side options, which are efficiency, electrification, and to some extent a switch to either biomass or hydrogen. So this is what we have to do no matter what, and achieve significant reductions by 2030.
Switching to biomass or hydrogen is in your most robust policy line?
Actually, electrification is most robust, but this is
Okay.
biomass and hydrogen is another important component.
Okay.
And to achieve that, of course, you need some policy instruments, and the most important, the most powerful one is to introduce a price on CO2. This is what is key to achieve that, and actually not only in some sectors or in some regions of the world. You have to go as comprehensive as possible to get to this goal of near zero emissions in the long term.
That was a very good, succinct answer to a very good question. Thank you. Somebody here wanted in the audience. Here we go.
Hi, my name is Ask. I'm a student at NTNU. I've actually got two questions. The first one is, when you're looking at bio-CCS, I see numbers that the land area necessary for this is the equivalent of more than India. So how do you really, and then use the whole land area for bio-CCS? So how is this even realistic at all? And also today you see like the Norwegian government are now really looking at pulling out of the development of CCS. So who are the main players left in the development of the technology itself? Because this is really, really tech optimistic when you see that, okay, today we have amine technology, that's it. So how are you really going to capture this carbon, and where are you going to put it? So it's really just like a castle in the sky, the whole thing, unless you have the technology here.
Great questions. Were big assumptions, basically.
I think these are all fair points. And the point that we're trying to make is we're not advocating any of these scenarios or any of these approaches. We just say, if you want to go for 1.5 degrees, and from a geophysical point of view, as I hopefully convinced you in my first slide, there are good arguments for going as stringent as possible with regards to your long-term temperature target. We try to spell out what are the implications of getting there, and what are the main trade-offs. And clearly the big trade-off, like the single biggest trade-off that we see are clearly these biomass deployment numbers, but there also it's important to kind of be more subtle in the discussion. And like the size of India type of numbers, this is typically what we see in terms of land requirements by the end of the century, because these biomass deployment pathways typically have a pattern of really taking off over the course of the second half of the century. And they are.
But that's when you most need it, isn't it? So
right. But well,
realistic
this is
isn't it?
like the underlying scenarios are built with explicit land use modeling, where you, for example, you put into the modeling food demands, you put into the modeling either exogenous assumptions or like some endogenous approaches to represent how yield improvements develop over time. And what really helps this effort is that in our standard scenarios, population is expected to decline over the course of the second half of the century. And at the same time, you have these yield improvements, and this is what creates a space for a certain amount of land dedicated to biomass. But of course, there are trade-offs. There are trade-offs with food prices, and there are trade-offs with biodiversity, and this is very important to spell out.